The material. There's quite a bit to review, so this is just the first video of a few. We're going to touch a little bit about the introduction of that whole subject, and also what is the whole thing with the Jablonski diagram, which is super important to understand. Not only is it well represented in questions, I have seen more than once an instance in an exam where they asked to draw it. So we're going to do just that as well. Let's get started. This is a copy-paste from Wikipedia, and I always say that I don't really like to use material from Wikipedia as much as other people, but I do find their definitions very easy and comprehensive. So fluorescence is the emission of light by a substance that has absorbed light or other electromagnetic radiation, which is essentially somewhat redundant. Electromagnetic radiation can be considered as light. So what we need to understand is that there are molecules that are fluorophores. Fluorophores are molecules that can absorb light or electromagnetic radiation and emit light. That is specific characteristics of that specific molecules. And different fluorophores can absorb different spectrum of lights. Each fluorophore has specific wavelengths that they can absorb. That's called their absorption. The absorption spectrum. And accordingly, they have a specific spectrum that they can emit light in, and that is called the emission spectrum. The emission spectrum. You will also see oftentimes the absorption spectrum referred to as the excitation spectrum, which is really the same thing. What's important to understand is that if I have this fluorophore here, and I know this fluorophore can absorb light and emit light, what I also need to know is what wavelengths of light I can shine on this fluorophore to get back that emission. It's important to understand that you can't excite a fluorophore molecule with any wavelength of light. It's specific for every molecule. Let's just say this specific molecule can be excited with blue light and would emit, let's just say, a green light. This is a specific character for this specific fluorophore. And that's really what we're looking at understanding. And we're going to talk a little bit more at length about absorption and emission spectrums later on. All right, so let's keep going and talk a little bit about the Jablonski diagram. I'm going to talk about it at length and make sure it's very well explained and well understood. Just to touch base with you what I mean, I'm talking about this little guy right here. And all the other sub-depictions, this depiction, this depiction, this depiction, this depiction, it's all the same diagram. It is the Jablonski diagram. And that diagram is the essence of fluorescence, of understanding what is going on. We already know that we can use light, or we can use photons to excite the molecule. And namely, we excite the electrons in the molecule. Electrons are excited. The electrons absorb the energy. Absorb the energy. Never follow my footsteps as far as spelling. What I'm going to do right now is I'm going to draw the Jablonski diagram from scratch, mainly because I find it easier for other students to look at diagrams that were freshly constructed, and also being that they sometimes ask for students to draw it, so I'm going to do just that. I drew the base level here. This is the ground level, or noted S0. This is the level which electrons are ideally at and will aspire to get to. This is the stable level. And I'm going to have several excited levels. So say this is my first excited level, and this is my second excited level. Now, we already discussed these are electronic transitions. And also in between them, in between these electronic transitions, we have rotation and vibration levels as well. Meaning that the molecule, the fluorophore, can lose some energy in vibration or rotation, and not only having electrons jump back and forth in electronic transitions. And those are the lines that you see. Let's look at those lines that you see here. And these lines basically fill in the gaps between these electronic transition levels. Perfect. So we have the first excited level, the second excited level, and I'm going to just work with these two before I get into the other type of levels that we have. But essentially, let's see what's going on. Let's just say I have my electron. It's green right here, and I had a photon of light that is in the absorption spectrum of the fluorophore, which means the fluorophore can absorb it. And that electron shot up, got excited, got some energy and shot up. And now it's shot up and it's right around here. The interesting thing is, and this is an important idea, is that as soon as electrons get excited, the first thing that happens after they get excited is that they rotate or vibrate down to the closest level, or the closest set electronic level. Let's just say that this electron shot up here. The first thing that would happen is that it's going to vibrate and rotate down to get to this level. You can consider these level an intermediate semi-stable levels, and the electron is not going to be able to stay in these intermediate rotation vibration energy levels. It's going to have to get to one of these electronic set levels. And it's quite important to label this, so we're going to do that. This is called internal conversion. And internal conversion follows a rule, and it's quite important to understand because they often ask about this rule, Cash's rule. And it's just the same thing I just stated, that an electron would always aspire to get to semi-stable set level after being excited. This is essentially the internal conversion is a follow-up idea or the implication of Cash's rule, and that's important to understand. Now after that, my electron is, you can say, has some potential energy at this point, and we always said that these electrons would aspire to get back to the stable ground level. I'm going to just label this here. This is the ground level. All right, this is the ground level, and these are the excited levels. I'm going to just put it here. Excited. Perfect. Now, when we go down from a higher level to a ground level, we know that we're emitting energy. And that energy could be emitted as a photon. So if this little dude drops down here, it can emit a photon. Let's just say this is the color of the photon. And this photon would be in the emission, within the emission, always within the emission spectrum of that specific fluorophore. Whereas the photon that was exciting the fluorophore would always have to be within the absorption spectrum. And this is important to understand. Perfect. So I have my specific molecule was excited by a photon within the absorption spectrum of that specific fluorophore. One of my electrons dropped up, got excited, got some energy. Because it was in the intermediate vibration rotation levels, due to Cash's rule, it rapidly vibrated or rotated down to the first closest semi-stable level here, the semi-stable excited level here. And then after a while, and these are very short times, and we're going to mention what time frames we're talking about, this dude just dropped down and emitted the energy as a photon. And it's important to understand that this emission of a photon is called radiative relaxation. And just so you know what I'm talking about, this is perceived as KF. This is K fluorescence. This is the relaxation as far as fluorescence. And the KNR, the dropping down, in the KNR refers to a non-radiative relaxation, which means that we can have this little electron drop down and not emit a photon. This would be a non-radiative, or we're going to refer to it as non-radiative K, non-radiative form of relaxation. But it can also emit a photon, which is obviously a radiated form of relaxation. So we mentioned these transitions. Let's mention some time frames. And again, you would see these time frames cited slightly differently in different websites and articles, but the gist is the same. It is really quick. The absorption happens really rapidly, around 10 to the negative 15. And the internal conversion also happens very, very rapidly, 10 to the negative 13. And just to make it obvious, I'm talking about seconds here, 10 to the negative 15 and 10 to the negative 13 seconds. And we can have fluorescence, we're talking about radiative fluorescence relaxation, at around 10 to the negative 9 seconds, just around there. And now we understood that if we have a fluorophore that is excited by a photon that's within its absorption spectrum, one of the electrons is going to shoot up, it's going to get excited, essentially it's going to store some energy, it's going to lose some energy in internal conversion in a non-radiative fashion, and that's also something I should have mentioned. Internal conversion is rotation and vibration, it's non-radiative. We would not get a photon from internal conversion. And then it achieved a semi-stable status here in the first excited level. And obviously this can happen in the second excited level or the third excited level or whatever, and emitted a photon here. What's important to understand also is that if I have this electron here, let's say it's the same electron, it went through internal conversion, what it can do here, it can also vibrate a little bit and then stop here, and that from this point emit a photon. It's important to understand that the vibration rotational levels are intermediate levels that the electron can go through, and this is at random, entirely at random. What we also need to bear in mind, that if we have a photon that was emitted from this energy level, and a photon that was emitted from a bigger energy level, a bigger difference, this is going to be a more energetic photon than this. Or rather, this is going to have a higher frequency or a lower wavelength than this photon. And this should make sense because the more energy is associated with the transition, the more energy the photon is going to have. Okay, fair enough. So what I'm going to do now is I'm going